Tonight, we embark on a journey through time itself. We will follow the story of everything that exists, from the very first moment of creation to the emergence of the stars that now illuminate our night sky. This is not a tale of drama or excitement, but rather a calm progression through the most fundamental story ever told: the birth and early development of our universe. Our journey will unfold in perfect chronological order, beginning at time zero and moving forward through each critical phase of cosmic evolution. We will witness the universe's first fraction of a second, when the laws of physics themselves were being established. We will observe the cooling and expansion that allowed the first particles to form, and then the first atoms. We will experience the long darkness that followed, and finally, the ignition of the first stars. Each step in this cosmic timeline built upon the previous one, creating the foundations for everything we see today. The universe we inhabit is the result of billions of years of gradual change, each era flowing naturally into the next. As we trace this progression, we will maintain a steady pace, allowing each phase to reveal itself clearly and completely. This is a story that deserves patience, for it took nearly 14 billion years to unfold, and rushing through it would diminish its profound simplicity and elegance. The universe began as something unimaginably small and unimaginably dense. From this singular point, everything we know expanded outward in a process that continues to this day. But the early universe was nothing like the cosmos we observe now. There were no stars, no planets, no galaxies. There was not even empty space as we understand it. Instead, there was only energy, compressed into a region smaller than an atom, hotter than any temperature we can truly comprehend. Our journey through cosmic history will follow a precise timeline, moving from one era to the next in the exact sequence in which they occurred. We begin at the Planck epoch, the first instant after the Big Bang, when the universe was so small and so energetic that our current understanding of physics reaches its limits. From there, we will witness cosmic inflation, a period of exponential expansion that occurred in less than a second, but transformed the universe from something smaller than a proton into something the size of a grapefruit. Following inflation, we enter an era of cooling and particle formation. As the universe expanded, it cooled, allowing energy to condense into the first fundamental particles. Quarks and gluons filled the cosmos in a hot, dense soup. As cooling continued, these particles combined to form the first protons and neutrons, the building blocks of all atomic nuclei. The next major milestone comes during the era of Big Bang nucleosynthesis, when the first light atomic nuclei formed. For about 20 minutes, the universe was hot enough to fuse hydrogen into helium, but cool enough that these nuclei could survive. This process created nearly all the helium in the universe, along with trace amounts of lithium and beryllium. Our timeline then moves to recombination, approximately 380,000 years after the Big Bang, when electrons first combined with nuclei to form neutral atoms. This event released the cosmic microwave background radiation that we can still observe today, a faint glow that fills all of space and provides us with our oldest direct observation of the early universe. What followed was a period known as the Cosmic Dark Ages, lasting hundreds of millions of years. During this time, the universe contained only neutral hydrogen and helium atoms, with no sources of light. Gravity slowly pulled these atoms together, into increasingly dense clouds, setting the stage for the formation of the first stars. The end of the Dark Ages came with the ignition of population 3 stars, the first stars in cosmic history. These massive, pristine stars were composed only of hydrogen and helium, the elements created in the Big Bang. They lived brief, violent lives before exploding as supernovas, scattering heavier elements throughout space and providing the materials for the next generation of stars. Finally, we will witness the formation of the first galaxies, as groups of stars began to cluster together under the influence of gravity. These early galaxies were smaller and more irregular than the grand spiral and elliptical galaxies we see today, but they marked the beginning of the large-scale structure that shapes our universe. Throughout this journey, we will encounter moments that invite quiet contemplation. What does it mean for space itself to expand? How can we comprehend temperatures so extreme that atoms cannot exist? What was it like when the universe first became transparent to light? These questions do not demand immediate answers, but rather patient consideration as we move through each phase of cosmic development. Each era we explore built the foundation for the next. Without the precise conditions of Big Bang nucleosynthesis, the universe would not have the right proportion of hydrogen and helium for star formation. Without the cooling that enabled recombination, light could not travel freely through space. Without the gravitational collapse during the Dark Ages, there would be no dense regions where stars could ignite. The story we are about to tell is one of gradual transformation, of simple beginnings, leading to increasing complexity. It is a story that can be followed step by step without haste, allowing each phase to reveal its essential character. The universe itself took billions of years to reach the point where stars began to shine, and our exploration will honor that patient progression. As we begin this chronological journey, we do so with the understanding that we are tracing the history of everything that exists. Every atom in your body was forged in the nuclear furnaces of stars that formed billions of years ago. The light that allows you to see was first able to travel freely through space during the era of recombination. The very space you occupy has been expanding continuously since the moment of the Big Bang. At time 0, 13.8 billion years ago, the universe began. Not in empty space, but as space itself. Not with an explosion into existing volume, but as the creation of volume. In this first instant, everything that would ever exist was compressed into a region far smaller than a single atom, at temperatures exceeding 10 to the 32nd power Kelvin. This initial moment is called the Planck epoch, lasting until 10 to the negative 43rd seconds after the Big Bang. During this brief interval, the universe was so dense and so hot that the fundamental forces of nature as we understand them today did not yet exist as separate entities. Gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single primordial force. The temperature during the Planck epoch was approximately 10 to the 32nd power Kelvin. To put this in perspective, the core of the Sun reaches about 15 million Kelvin. The temperature at the end of the Planck epoch was more than 1 trillion times hotter than the Sun's core. At such temperatures, matter as we know it could not exist. Even the fundamental particles that make up atoms were beyond the reach of these extreme conditions. During this time, the universe was dominated by pure energy. The distinction between matter and energy had not yet become meaningful, as conditions were far too extreme for stable particles to form. Quantum effects dominated the behavior of space and time themselves. The smooth fabric of space-time that we observe today existed only as quantum fluctuations, tiny variations in the geometry of space that would later grow into the largest structures in the universe. As the Planck epoch ended, the universe began to cool as it expanded. This cooling allowed the first phase transitions to occur, separating the unified force into the distinct forces we observe today. First, gravity separated from the other forces, becoming the independent force that would later shape the large-scale structure of the universe. The remaining three forces, electromagnetism and the strong and weak nuclear forces, remained unified for a brief time longer. The end of the Planck epoch marked the beginning of our ability to describe the universe using known physics. Before this time, the conditions were so extreme that our current theories of gravity and quantum mechanics are insufficient to provide accurate descriptions. We must rely on theoretical extrapolations and speculative models to understand what might have occurred during those first fleeting moments. As the universe continued to expand and cool beyond the Planck epoch, it entered the grand unification epoch, lasting until 10 to the negative 36th seconds after the Big Bang. During this period, the strong nuclear force separated from the unified electro-weak force, leaving only electromagnetism and the weak nuclear force combined as a single entity. The separation of these forces released enormous amounts of energy, further driving the expansion and cooling of the universe. Each phase transition was accompanied by the creation of new particles and the establishment of new physical laws. What had begun as perfect unity gradually developed into the complex interplay of forces and particles that would govern all future cosmic evolution. Throughout these earliest moments, the universe remained completely opaque. The density was so high and the interactions between particles so frequent that light could not travel any meaningful distance before being absorbed or scattered. If it had been possible to observe the universe during this time, it would have appeared as a brilliant, uniform glow, brighter than any star, extending in all directions without variation. The expansion during these first fractions of a second was not uniform throughout space, but rather was driven by the immense energy density and the dynamic interplay between the emerging forces. Small quantum fluctuations in density began to grow, seeded by the fundamental uncertainty principle of quantum mechanics. These tiny variations would eventually become the seeds around which all large-scale structure would form. As the grand unification epoch came to an end, the universe stood poised for its next great transformation. The stage was set for a period of exponential expansion that would dwarf even the remarkable growth that had already occurred. In less than a second, cosmic inflation would take the universe from a size smaller than a proton to larger than a grapefruit, stretching the fabric of space-time itself and setting the initial conditions for everything that would follow. The forces of nature now existed as separate entities, each with its own character and domain of influence. Gravity would pull matter together across vast distances. The strong nuclear force would bind quarks into protons and neutrons. The electromagnetic force would govern the behavior of charged particles and light. The weak nuclear force would enable radioactive decay and certain types of particle interactions. From the perfect unity of the Planck epoch, the universe had evolved into a realm where diverse phenomena could begin to emerge. As the grand unification epoch ended, approximately 10 to the negative 36th seconds after the Big Bang, the universe underwent the most dramatic transformation in its entire history. This period, known as cosmic inflation, lasted for only a tiny fraction of a second, ending around 10 to the negative 32nd seconds after the Big Bang. Yet in this brief interval, the universe expanded by a factor of at least 10 to the 26th power, growing faster than the speed of light itself. The driving force behind inflation was a special type of energy field called the inflaton field. Unlike ordinary matter or radiation, this field possessed a unique property. It created a gravitational effect that was repulsive rather than attractive. As long as the inflaton field maintained its high energy state, it would cause space itself to expand exponentially, doubling in size every tiny fraction of a second. During inflation, the universe grew from a size smaller than a proton to larger than a grapefruit. This comparison understates the magnitude of the expansion, as the actual increase in volume was astronomical. Every point in space moved away from every other point at an accelerating rate, stretching the fabric of space-time itself. The expansion was not matter moving through existing space, but rather the creation of new space between every pair of points. This exponential expansion solved several puzzles that had troubled cosmologists. Before inflation was proposed, scientists wondered why the universe appeared so uniform in all directions, despite the fact that different regions of the observable universe had never been in contact with each other. Inflation explained this by proposing that all the regions we can observe today were once close together in thermal equilibrium before being stretched apart by the exponential expansion. The uniformity we observe in the cosmic microwave background radiation, which varies by only 1 part in 100,000 across the entire sky, is a direct consequence of inflation. Before inflation began, the tiny region that would become our entire observable universe was small enough that light could travel across it many times, ensuring thermal equilibrium and uniform temperature. Inflation then stretched this uniform region to encompass everything we can see today. As the universe expanded during inflation, its temperature dropped dramatically. The exponential stretching of space diluted the energy density, causing the temperature to fall from approximately 10 to the 27th power Kelvin at the beginning of inflation to about 10 to the 22nd power Kelvin at its end. Despite this cooling, the universe remained far too hot for any familiar particles to exist in stable form. Throughout the inflationary period, the universe remained dominated by the energy of the inflaton field itself. This field was not uniform, but contained tiny quantum fluctuations, microscopic variations in energy density that arose from the fundamental uncertainty principle of quantum mechanics. As space expanded, these quantum fluctuations were stretched to macroscopic scales, creating regions of slightly higher and lower energy density throughout the cosmos. These stretched quantum fluctuations became the seeds for all future structure formation in the universe, regions with slightly higher energy density would eventually become the locations where galaxies and galaxy clusters would form, while regions with lower density would become the vast empty spaces between them. In this way, the largest structures in the universe today can trace their origins back to quantum mechanical effects during the inflationary epoch. Near the end of inflation, the inflaton field began to decay, releasing its stored energy in the form of particles and radiation. This process, known as reheating, marked the transition from the inflationary epoch to the radiation-dominated epoch that would characterize the universe for hundreds of thousands of years to come. The energy that had driven the exponential expansion was converted into the hot, dense plasma of particles that would gradually cool and organize themselves into atoms, stars, and galaxies. The decay of the inflaton field did not happen all at once throughout the universe, but rather occurred region by region as the field reached the critical conditions for decay. This led to a brief period where some areas of the universe were still inflating, while others had already begun reheating. However, within our observable region, reheating was completed very quickly, establishing the initial conditions for the next phase of cosmic evolution. As inflation came to an end, the universe found itself in a very different state than when the process began. What had started as a tiny, dense region had become a vast expanse of space, filled with the products of the decaying inflaton field. The exponential expansion had created far more space than had existed before, space that would continue to expand at a more modest rate, governed by the ordinary gravitational effects of matter and radiation. The end of inflation marked the beginning of the hot Big Bang phase that most people associate with the creation of the universe. From this point forward, the universe would be dominated by ordinary matter and radiation, gradually cooling as it expanded according to the normal laws of thermodynamics and gravity. The stage was now set for the formation of the first fundamental particles and the beginning of nuclear physics on a cosmic scale. Following the end of cosmic inflation and the subsequent reheating, the universe entered a new phase characterized by the formation of the first stable particles. This period, known as the quark epoch, lasted from approximately 10 to the negative 12 seconds to 10 to the negative 6 seconds after the Big Bang. During this time, the universe cooled sufficiently to allow the fundamental building blocks of matter to condense out of pure energy. At the beginning of the quark epoch, temperatures had dropped to around 10 to the 15th power Kelvin, still incredibly hot by any standard we can imagine, but cool enough for quarks and gluons to exist as distinct particles. These particles filled the universe in the form of a quark-gluon plasma, a state of matter so exotic that it can only be recreated today in the most powerful particle accelerators on Earth. Quarks are the fundamental constituents of protons and neutrons, but in the early universe, they existed freely in the cosmic plasma. There were 6 types of quarks, though only the 2 lightest varieties, up quarks and down quarks, would play important roles in forming ordinary matter. The other 4 types of quarks were too heavy to survive long in the cooling universe and quickly decayed into lighter particles. Gluons served as the carriers of the strong nuclear force, binding quarks together through interactions of extraordinary strength. In the quark-gluon plasma, These gluons mediated constant interactions between the quarks, creating a dynamic, turbulent medium unlike anything that exists in the universe today. The density was so high that every quark was in constant interaction with countless others, creating a truly collective state of matter. As the universe continued to expand and cool, it underwent a critical phase transition known as the QCD phase transition, named after quantum chromodynamics, the theory that describes the strong nuclear force. This transition occurred when the temperature dropped to approximately 1 trillion Kelvin, about 100 million times hotter than the core of the Sun. At this critical temperature, quarks and gluons could no longer exist as free particles and were permanently confined within composite particles called hadrons. The most important hadrons formed during this transition were protons and neutrons, collectively known as nucleons. Protons are composed of 2 up quarks and 1 down quark, bound together by gluons. Neutrons contain 1 up quark and 2 down quarks, also held together by the strong nuclear force. These particles would become the building blocks of all atomic nuclei, and therefore of all ordinary matter in the universe. The formation of protons and neutrons was not immediate but occurred over a brief period, as the temperature fell below the critical threshold. During this time, the universe was filled with a mixture of free quarks and gluons alongside the newly formed nucleons. Gradually, as cooling continued, all the free quarks became bound within hadrons, and the quark-gluon plasma disappeared forever from the universe. Along with protons and neutrons, the cooling universe also produced large numbers of other hadrons, including particles called pions and kaons. However, these particles were unstable and decayed rapidly into lighter particles, primarily electrons, neutrinos, and photons. By the end of the quark epoch, the universe was dominated by protons, neutrons, electrons, neutrinos, and photons, the fundamental constituents that would shape all future cosmic evolution. The ratio of protons to neutrons was not equal during this period. At temperatures above 10 billion Kelvin, protons and neutrons were in thermal equilibrium, with roughly equal numbers of each. However, as the temperature dropped below this threshold, the equilibrium shifted in favor of protons because they are slightly lighter than neutrons. By the end of the quark epoch, there were approximately 7 protons for every neutron in the universe. This imbalance between protons and neutrons would prove crucial for the future composition of the universe. The excess of protons meant that hydrogen, the simplest nucleus consisting of a single proton, would become the most abundant element. The neutrons, meanwhile, would mostly be incorporated into helium nuclei during the next phase of cosmic evolution, when the universe would become cool enough for nuclear fusion to occur. Throughout the quark epoch, the universe remained completely opaque to light. The density of particles was so high that photons could not travel any significant distance without being absorbed or scattered. The universe was filled with a brilliant, uniform glow, but this light was trapped within the cosmic plasma, unable to escape and travel freely through space. As the quark epoch drew to a close, the fundamental particles of matter had been established, but atoms had not yet formed. Electrons remained free, unbound to any nucleus, while protons and neutrons existed as isolated particles in the cosmic plasma. The temperature was still far too high for electrons to be captured by nuclei, and the density was too low for nuclear fusion to occur. The universe now consisted of a hot, dense soup of fundamental particles, all in constant thermal motion and frequent interaction with one another. This marked the end of the exotic physics that had characterized the earliest moments of cosmic history. From this point forward, the universe would be governed by the familiar laws of nuclear physics, electromagnetism, and gravity that we can study and understand using terrestrial experiments and observations. As the universe continued to expand and cool beyond the quark epoch, it reached a critical juncture when nuclear fusion could begin on a cosmic scale. This period, known as Big Bang nucleosynthesis, commenced approximately 1 second after the Big Bang and lasted until about 20 minutes later. During this brief window, the universe synthesized most of the helium that exists today, along with smaller amounts of deuterium, lithium, and beryllium. At the beginning of nucleosynthesis, the temperature had dropped to approximately 10 billion Kelvin, cool enough for protons and neutrons to stick together when they collided, but still hot enough to maintain the high energy conditions necessary for nuclear fusion reactions. The universe was filled with a dense plasma of protons, neutrons, electrons, and photons, all in thermal equilibrium at this extraordinarily high temperature. The first nuclear reaction to occur was the fusion of a proton and neutron to form deuterium, a heavy isotope of hydrogen. This reaction had been prevented earlier by the high temperature, which provided enough energy to immediately break apart any deuterium nuclei that formed. But as the universe cooled below 10 billion Kelvin, deuterium nuclei could survive long enough to participate in further nuclear reactions. Once deuterium became stable, it quickly participated in additional fusion reactions. Deuterium nuclei fused with protons to form helium-3, and they also fused with neutrons to form tritium, a radioactive isotope of hydrogen. These reactions occurred rapidly because the universe contained enormous numbers of protons and neutrons, all moving at high speeds due to the extreme temperature. The most important fusion chain led to the production of helium-4, the most common isotope of helium. This occurred when deuterium nuclei fused together, or when helium-3 fused with neutrons, or through several other reaction pathways. Helium-4 nuclei are particularly stable, so once they formed, they persisted throughout the remainder of nucleosynthesis and beyond. The efficiency of Big Bang nucleosynthesis was remarkable. In just 20 minutes, approximately 25% of all the normal matter in the universe was converted from hydrogen into helium. This represents one of the most dramatic chemical transformations in cosmic history, changing the fundamental composition of the universe in a very short time. The process was largely determined by the ratio of protons to neutrons that had been established during the previous epoch. With about 7 protons for every neutron, and with nearly all neutrons becoming incorporated into helium-4 nuclei, the final result was a universe composed of roughly 75% hydrogen and 25% helium by mass. This ratio has remained essentially constant throughout cosmic history. Small amounts of other light elements were also produced during nucleosynthesis. Deuterium was created in abundance, but was mostly consumed in further reactions, leaving only a tiny fraction to survive to the present day. Lithium-7 was produced in much smaller quantities through a series of complex reactions involving helium-4 and tritium. Trace amounts of beryllium-7 were also formed, though this isotope is radioactive and eventually decayed into lithium-7. The production of elements heavier than lithium was prevented by a gap in nuclear stability. There are no stable nuclei with 5 or 8 nucleons, which meant that fusion chains could not proceed beyond lithium and beryllium. Creating carbon and heavier elements would require the much more complex processes that occur inside stars, involving triple alpha reactions and other mechanisms that cannot operate in the conditions of the early universe. As nucleosynthesis proceeded, the universe continued to expand and cool. The temperature dropped steadily, and the density of particles decreased correspondingly. These changing conditions gradually brought the fusion reactions to a halt. By 20 minutes after the Big Bang, the temperature had fallen below 1 billion Kelvin, too cool for further nuclear fusion to occur at significant rates. The end of Big Bang nucleosynthesis left the universe with its final primordial composition. Approximately 75% hydrogen, 25% helium, and tiny traces of deuterium, lithium, and beryllium. This chemical composition would remain essentially unchanged for hundreds of millions of years until the first stars began to synthesize heavier elements in their nuclear cores. The success of Big Bang nucleosynthesis provides one of the strongest pieces of evidence for the hot Big Bang model of cosmic evolution. The observed abundances of light elements in the universe match the theoretical predictions with remarkable precision, confirming that the universe was indeed once hot and dense enough for widespread nuclear fusion to occur. During this entire period, the universe remained opaque to light. Although nuclear fusion was creating helium nuclei, electrons were still free particles, unbound to any nucleus. The high temperature prevented electrons from being captured by nuclei to form neutral atoms. Photons were constantly absorbed and re-emitted by the free electrons, keeping light trapped within the cosmic plasma. The completion of Big Bang nucleosynthesis marked the end of nuclear activity in the early universe. From this point forward, the cosmic evolution would be dominated by the gravitational interactions of the matter that had been created, rather than by nuclear physics. The stage was set for the next major milestone, the formation of the first neutral atoms and the release of the cosmic microwave background radiation. What would it mean to witness a universe where nuclear fusion occurred everywhere at once, where every cubic centimeter of space was a stellar core creating helium from hydrogen? For 20 minutes, the entire universe was a single, vast fusion reactor, transforming the primordial matter into the elements that would eventually form stars, planets, and life itself. After the completion of Big Bang nucleosynthesis, the universe entered a long period of gradual cooling and expansion. For approximately 380,000 years, the cosmos remained filled with a hot plasma of nuclei and free electrons, opaque to light and uniform in temperature throughout. This period came to an end during an epoch known as recombination, when electrons first combined with nuclei to form neutral atoms, fundamentally changing the nature of the universe. At the beginning of this era, the universe was still far too hot for neutral atoms to exist. The temperature of approximately 3000 Kelvin was sufficient to immediately ionize any atoms that might form, keeping electrons and nuclei separate. Photons were constantly interacting with the free electrons through a process called Thomson scattering. which prevented light from traveling any significant distance through the cosmic plasma. As the universe continued to expand, its temperature dropped steadily according to the laws of thermodynamics. The expansion stretched the wavelengths of all electromagnetic radiation, cooling it in the process. Simultaneously, the density of matter decreased as the same number of particles occupied an ever-increasing volume of space. These two effects combined to gradually reduce the energy available to maintain the ionization of hydrogen atoms. The critical temperature for recombination was reached when the universe had cooled to approximately 3,000 Kelvin, about half the temperature of the sun's surface. At this point, the thermal energy of the particles was no longer sufficient to immediately ionize hydrogen atoms as they formed. Electrons began to be captured by protons, creating the first neutral hydrogen atoms in cosmic history. Recombination did not occur instantaneously throughout the universe, but rather proceeded as a gradual process over several thousand years. The universe slowly transitioned from a state where most electrons were free to one, where most electrons were bound within neutral atoms. This transition was not uniform in space or time, creating subtle variations in the timing of recombination in different regions. The formation of neutral atoms had a profound effect on the behavior of light in the universe. Free electrons are very effective at scattering photons, but neutral atoms are largely transparent to most wavelengths of light. As recombination proceeded, the universe gradually became transparent, allowing photons to travel freely through space for the first time since the earliest moments after the Big Bang. The last photons to be scattered by free electrons before recombination was completed now form the cosmic microwave background radiation that we observe today. This radiation has been traveling through space for over 13 billion years, carrying with it a snapshot of the universe as it appeared when it first became transparent. The cosmic microwave background represents our oldest direct observation of the early universe. When the cosmic microwave background was first emitted, it had a temperature of approximately 3,000 Kelvin and glowed with the warm light of heated matter. However, the expansion of the universe has stretched these photons over billions of years, cooling them to their present temperature of just 2.7 Kelvin above absolute zero. What was once visible light has been red-shifted into the microwave portion of the electromagnetic spectrum. The cosmic microwave background is remarkably uniform across the entire sky, varying in temperature by only about 1 part in 100,000. This uniformity confirms that the universe was in thermal equilibrium at the time of recombination, supporting the predictions of the Big Bang model and cosmic inflation theory. The tiny variations that do exist represent the seeds of all future structure formation in the universe. These minute temperature fluctuations in the cosmic microwave background correspond to regions of slightly higher and lower density in the primordial universe. Areas with higher density were slightly cooler because gravity was beginning to compress them, while lower density regions were slightly warmer as they expanded more freely. These density variations would eventually grow under the influence of gravity to become the galaxies and galaxy clusters we observe today. The precision with which we can measure the cosmic microwave background has provided cosmologists with detailed information about the fundamental parameters of the universe. The pattern of temperature fluctuations reveals the geometry of space, the total amount of matter and energy in the universe, and the rate of cosmic expansion. These measurements have confirmed our understanding of cosmic evolution with remarkable accuracy. During recombination, the universe was composed almost entirely of hydrogen and helium atoms, with trace amounts of deuterium and lithium. There were no heavier elements, no molecules, and no complex chemistry. The cosmos was filled with a diffuse gas of simple atoms at a temperature that would be considered quite warm by terrestrial standards, but was cold enough to allow the first chemical bonds to begin forming. The completion of recombination marked a fundamental transition in cosmic evolution. For the first time since the earliest moments after the Big Bang, light could travel freely through space. The universe, which had been opaque and uniform, suddenly became transparent and structured. The stage was now set for gravity to begin gathering matter into increasingly dense concentrations, eventually leading to the formation of the first stars. As recombination ended, the universe entered what cosmologists call the Dark Ages, a period lasting several 100 million years, during which no sources of light existed. The cosmic microwave background continued to cool and redshift, while the neutral hydrogen and helium atoms slowly began to cluster under the influence of gravity. It would be many millions of centuries before the first stars would ignite and begin to illuminate the cosmos once again. The cosmic microwave background radiation continues to fill all of space today, a faint echo of the time when the universe first became transparent. Every cubic centimeter of space contains about 400 photons from this ancient light, cooled by cosmic expansion, but still carrying information about the universe as it existed nearly 14 billion years ago. Following recombination, the universe entered its longest and perhaps most mysterious period, the cosmic Dark Ages. This era lasted from approximately 380,000 years after the Big Bang until roughly 150 million years later, when the first stars began to shine. During this time, the universe was filled with neutral hydrogen and helium atoms, but contained no sources of light apart from the steadily cooling cosmic microwave background radiation. The universe at the beginning of the Dark Ages was a very different place from the cosmos we observe today. The temperature of the cosmic microwave background was still several hundred Kelvin, warm enough to heat the gas throughout space to temperatures well above the freezing point of water. However, this warmth was gradually diminishing as the expansion of the universe continued to stretch and cool the ancient photons from recombination. With no stars yet formed, the only matter in the universe consisted of the primordial elements created during Big Bang nucleosynthesis. Approximately 75% of all atoms were hydrogen, 25% were helium, and tiny fractions consisted of deuterium and lithium. These atoms were distributed almost uniformly throughout space, with only the slightest variations in density corresponding to the temperature fluctuations observed in the cosmic microwave background. During the early part of the Dark Ages, the universe was actually not completely dark. The cosmic microwave background radiation, though steadily cooling, still provided a faint glow throughout all of space. As this radiation cooled from thousands of Kelvin to hundreds of Kelvin, it shifted from the infrared portion of the electromagnetic spectrum toward longer wavelengths, eventually becoming too cool to provide any significant illumination. The most important process occurring during the Dark Ages was the gradual gravitational collapse of matter into increasingly dense structures. The tiny density variations that had been imprinted during cosmic inflation and preserved through recombination began to grow under the influence of gravity. Regions that were slightly denser than average attracted additional matter, while regions that were slightly less dense became increasingly empty. This gravitational collapse proceeded very slowly at first. The density variations were extremely small, only about 1 part in 100,000, so the gravitational forces were correspondingly weak. However, as the universe continued to expand and cool, these small perturbations gradually amplified, creating a hierarchical network of structure formation that would eventually lead to galaxies, stars, and planets. Dark matter played a crucial role during the Dark Ages, though its presence was invisible to any hypothetical observers. This mysterious form of matter, which interacts only through gravity, had been growing its own structure since recombination began. Dark matter halos formed first, creating the gravitational wells into which ordinary matter would eventually fall. These invisible scaffolding structures guided the formation of all visible matter in the universe. As the Dark Ages progressed, clouds of hydrogen and helium began to collect in the deepest gravitational wells created by dark matter. These gas clouds were initially quite warm, with temperatures of several thousand Kelvin, heated by the gravitational energy released as matter fell inward. However, the gas gradually cooled through the emission of infrared radiation, allowing the clouds to contract further under their own gravity. The cooling process was facilitated by trace amounts of molecular hydrogen that formed through chemical reactions between hydrogen atoms. Even though molecular hydrogen made up only a tiny fraction of all matter, it was much more efficient at radiating energy than atomic hydrogen, allowing the gas clouds to cool to temperatures of just a few hundred Kelvin. This cooling was essential for gravitational collapse to continue. Throughout the Dark Ages, the universe was filled with the sounds of gravitational collapse, though no ears existed to hear them. As gas fell into dark matter halos and compressed under gravity, it generated acoustic waves that propagated through the cosmic medium. These sound waves left their imprint on the distribution of matter, creating patterns that would influence the formation of stars and galaxies millions of years later. The end of the Dark Ages was not marked by a single dramatic event, but rather by the gradual onset of star formation as the densest gas clouds finally collapsed to the point where nuclear fusion could begin. The first regions to reach this critical threshold were the centers of the most massive dark matter halos, where gravitational forces were strongest and gas densities were highest. As the Dark Ages drew to a close, the universe had been transformed from a nearly uniform distribution of atoms into a complex network of dark matter halos filled with cooling gas clouds. The largest of these structures contained millions or even billions of times the mass of our Sun, concentrated into regions that would soon become the first galaxies. The stage was set for the ignition of the first stars and the beginning of a new era in cosmic evolution. The Dark Ages represent a period of patient preparation, during which gravity slowly organized the raw materials created in the Big Bang into the structures that would eventually become the beautiful and complex universe we observe today. Though no light was generated during this time, the foundations were being laid for all the stellar fireworks that would follow. What would it have been like to experience a universe with no stars, no galaxies, and no sources of light except the fading glow of creation itself? This was a cosmos of pure potential, where every atom carried within it the promise of future complexity, waiting patiently for gravity to gather them into the first stellar nurseries. The transition from the Dark Ages to the era of star formation was gradual and uneven. Different regions of the universe reached the critical conditions for star formation at different times, depending on the local density of dark matter and the efficiency of gas cooling. The first stars did not appear simultaneously across the cosmos, but rather emerged one by one in the deepest gravitational wells, like fireflies, beginning to glow at twilight. Approximately 150 million years after the Big Bang, the universe experienced its second great illumination. The first was the cosmic microwave background, released when the universe became transparent during recombination. The second came with the ignition of the first stars, marking the end of the cosmic dark ages and the beginning of what astronomers call the Age of Reionization. These first stars, known as population 3 stars, were unlike any stars that exist in the universe today. They formed from the pristine gas created during Big Bang nucleosynthesis, composed almost entirely of hydrogen and helium, with only trace amounts of lithium. No carbon, oxygen, silicon, or iron existed in their composition, elements that are essential for the formation of modern stars, planets, and life itself. The absence of heavy elements had profound consequences for how these first stars formed. In the present-day universe, elements like carbon and oxygen help cooling gas clouds by efficiently radiating away thermal energy. This cooling allows gas clouds to fragment into many smaller pieces, each of which can collapse to form individual stars of moderate mass. Without these cooling agents, the primordial gas clouds could not fragment as efficiently. As a result, population 3 stars were massive beyond anything we observe in the modern universe. While typical stars today have masses similar to our Sun, or perhaps a few times larger, the first stars contained 50 to 100 times as much matter as our Sun, and some may have been even more massive. These stellar giants were powered by nuclear fusion processes that proceeded at extraordinary rates due to their enormous mass and correspondingly high core temperatures. The formation of a population 3 star began when a primordial gas cloud, cooled by molecular hydrogen emission and compressed by gravitational collapse, reached a critical density and temperature. At the center of the collapsing cloud, conditions became extreme enough for nuclear fusion to begin. The first fusion reactions converted hydrogen into helium, releasing enormous amounts of energy in the process. The nuclear fires at the center of these massive stars burned with incredible intensity. Core temperatures reached over 100 million Kelvin, far hotter than the cores of modern stars. The fusion rate was so high that these stellar giants shone with the brightness of millions of suns, illuminating their surroundings with ultraviolet radiation intense enough to ionize hydrogen atoms across vast regions of space. Population 3 stars lived fast and died young. While our sun will burn steadily for approximately 10 billion years, the first stars exhausted their nuclear fuel in just a few million years. Their enormous mass meant they burned through their hydrogen supplies at prodigious rates, racing through their entire life cycles in a cosmic instant. As these massive stars aged, they began to synthesize elements heavier than helium through nuclear fusion in their cores. Carbon was created through the triple alpha process, where 3 helium nuclei combined to form a carbon nucleus. Oxygen formed when carbon nuclei fused with additional helium. Silicon, sulfur, and iron were produced through successive fusion reactions involving ever heavier elements. The cores of population 3 stars became cosmic element factories, creating for the first time in the universe's history the chemical elements that would prove essential for planet formation and the development of life. However, these newly forged elements remained locked within the stellar cores, unable to escape into the broader universe, while the stars continued to shine. The death of population 3 stars was as spectacular as their lives had been brief. When these massive stars exhausted their nuclear fuel, they could no longer generate enough outward pressure to counteract their own gravitational pull. The cores collapsed catastrophically in less than a second, triggering explosions of unimaginable violence known as pair instability supernovas. These explosions were so energetic that they completely disrupted the stars, leaving no remnant behind. The entire mass of the star, including all the heavy elements forged in its core, was ejected into space at velocities of thousands of kilometers per second. For the first time in cosmic history, elements heavier than lithium began to enrich the interstellar medium. The energy released by population 3 supernovas was sufficient to heat and ionize hydrogen gas across volumes of space containing millions of stellar masses. The shock waves from these explosions propagated outward at enormous speeds, compressing nearby gas clouds and sometimes triggering the formation of new stars. The universe began to develop a complex ecology of stellar birth and death. The ultraviolet radiation from population 3 stars had an equally important impact on their surroundings. These stars emitted such intense ultraviolet light that they began to ionize the neutral hydrogen that had filled the universe since recombination. This process, known as reionization, gradually transformed the universe from a realm of neutral atoms back into a plasma of ions and free electrons. Reionization did not occur uniformly throughout space, but rather proceeded in an irregular pattern. Around each population 3 star, a bubble of ionized gas expanded outward at nearly the speed of light. These ionized bubbles eventually merged with one another, creating an increasingly connected network of ionized regions separated by neutral gas. The universe began to resemble a cosmic Swiss cheese, with holes of ionized gas expanding within the neutral medium. The first stars also began the process of chemical evolution that would eventually lead to the formation of planets and life. Each population 3 supernova dispersed newly created elements into the surrounding gas, increasing the metallicity, the abundance of elements heavier than helium, of the interstellar medium. This enriched gas would serve as the raw material for the next generation of stars. Population 3 stars played a crucial role in establishing the large-scale structure of the universe. Their intense radiation and violent deaths created feedback effects that regulated star formation in their vicinity. Some regions experienced enhanced star formation as shock waves compressed nearby gas clouds, while others were effectively sterilized as intense radiation dispersed potential stellar nurseries. The era of population 3 stars represents a bridge between the simple, pristine universe that emerged from the Big Bang and the chemically rich cosmos that would eventually harbor planets and life. These massive, short-lived stellar giants were the universe's first attempts at creating complexity from simplicity, transforming primordial hydrogen and helium into the full periodic table of elements. Although population 3 stars no longer form in the present-day universe, their legacy continues to shape cosmic evolution. Every atom of carbon in our bodies, every molecule of oxygen in our atmosphere, and every grain of silicon in the Earth's crust can trace its origins back to the nuclear furnaces of these ancient stellar giants. They were the ancestors of all complexity in the universe. Born as population 3 stars continued to ignite throughout the universe, their combined effects began to transform the cosmic landscape in ways that went far beyond the production of heavy elements. The intense radiation, powerful stellar winds, and catastrophic supernovas of these massive stars created feedback processes that regulated star formation and began to organize matter into the first galactic structures. This marked the beginning of the cosmic renaissance, a period when the universe transitioned from isolated stellar formation to the emergence of complex, gravitationally bound systems of stars. The first galaxies were very different from the majestic spiral and elliptical galaxies that dominate the present-day universe. These primordial galactic systems were small, irregular, and chaotic, containing perhaps a few million stars scattered throughout regions spanning several thousand light-years. They formed within the deepest gravitational wells created by dark matter, where the density of ordinary matter was highest and the conditions for star formation were most favorable. The formation of the first galaxies was intimately connected to the hierarchical growth of dark matter structure. As the universe evolved, smaller dark matter halos merged together to form progressively larger structures. Each merger brought together not only dark matter but also the gas and stars that had accumulated within the merging halos. This process of gradual assembly would eventually build the massive galaxies we observe today. Within these early galactic systems, star formation proceeded in bursts, rather than the steady, sustained process observed in modern galaxies. The lack of heavy elements meant that gas cooling was less efficient, leading to irregular and sporadic episodes of stellar birth. When conditions were right, large regions of gas would collapse simultaneously, creating clusters of massive stars that would live briefly and die violently, enriching their surroundings with newly forged elements. The supernova explosions from population 3 stars had profound effects on their host galaxies. The energy released by these explosions was often sufficient to expel large quantities of gas from the shallow gravitational wells of the first galaxies. This feedback process regulated star formation by removing the raw material needed for new stars, preventing the first galaxies from growing too rapidly or becoming too massive. However, the same supernovas that limited galactic growth also provided the seeds for future complexity. The heavy elements dispersed by population 3 stars began to change the character of star formation throughout these early galaxies. Gas clouds enriched with carbon, oxygen, and other elements could cool more efficiently, allowing them to fragment into smaller pieces and form stars of lower mass than their population 3 predecessors. This transition marked the beginning of population 2 star formation, the creation of stars from gas that had been enriched with heavy elements by previous generations of stellar nucleosynthesis. Population 2 stars were smaller, longer-lived, and more similar to the stars we observe in the present-day universe. They could burn steadily for billions of years, providing stable sources of energy that would prove essential for the development of planetary systems and life. The first galaxies also began to exhibit the complex internal structure that characterizes galactic systems. Rotating disks of gas and stars formed within some systems, while others remained irregular and chaotic. Central regions became denser and more active, with higher rates of star formation and more frequent stellar interactions. The seeds of galactic nuclei were planted, though the supermassive black holes that power modern galactic centers had not yet formed. During this period, the universe began to develop its first generation of chemical gradients, with some regions becoming more enriched with heavy elements than others. Galaxies that experienced more vigorous star formation became more chemically evolved, while regions between galaxies remained relatively pristine. This spatial variation in chemical composition would have lasting effects on subsequent cosmic evolution. The ultraviolet radiation from the first galaxies continued the process of reionizing the universe that had begun with individual population 3 stars. The combined output from millions of hot young stars created extensive ionized regions around each galaxy, eventually connecting to form a cosmic web of ionized gas. By approximately 1 billion years after the Big Bang, the reionization of the universe was nearly complete, transforming the cosmos from a realm of neutral hydrogen back into the ionized plasma state it maintains today. The first galaxies also began to exhibit the phenomena of galactic winds, outflows of gas, driven by the combined effects of stellar radiation and supernova explosions. These winds carried newly synthesized elements far beyond the boundaries of their host galaxies, enriching the intergalactic medium and providing the raw materials for star formation in other systems. The universe began to develop a complex ecology of matter exchange between galaxies and their surroundings. As the first galaxies continued to grow and evolve, they began to influence the formation of subsequent generations of galactic systems. Their intense radiation could suppress star formation in nearby regions by heating and ionizing potential stellar nurseries. Conversely, their gravitational effects could trigger star formation by compressing nearby gas clouds. The universe was becoming an increasingly interactive and interconnected system. The merger of early galaxies became an important driver of cosmic evolution during this period. When two small galaxies encountered each other, their gravitational interaction could trigger intense bursts of star formation as gas clouds collided and compressed. These merger-induced starbursts created some of the most luminous objects in the early universe, shining brightly enough to be observed by modern telescopes across billions of light years. The formation of the first galaxies represented a fundamental transition in the character of the universe. What had begun as a smooth, nearly uniform distribution of matter had evolved into a complex network of gravitationally bound structures, each containing millions of stars and vast quantities of gas. The stage was set for the continued growth of cosmic complexity through billions of years of galactic evolution. The legacy of the first galaxies extends to the present day. Many of the galaxies we observe in the modern universe are descendants of these early systems, grown large through billions of years of star formation, gas accretion, and galactic mergers. The chemical elements forged in their first generations of stars continue to enable the formation of planets and the development of life throughout the cosmos. As the first galaxies continued to form and evolve, the universe began to reveal an even grander pattern of organization. The same gravitational processes that had created galaxies from individual stars began to operate on much larger scales, drawing galaxies together into clusters and clusters into superclusters, creating a vast cosmic web that spans the entire observable universe. This process of large-scale structure formation represents one of the most remarkable aspects of cosmic evolution, transforming a nearly uniform primordial medium into the complex hierarchical architecture we observe today. The foundation for this cosmic architecture had been laid during the earliest moments of the universe's existence. The quantum fluctuations that arose during cosmic inflation had created tiny variations in the density of matter, variations so small that they amounted to only 1 part in 100,000. Yet these microscopic seeds, stretched to cosmic proportions by the exponential expansion of space, would eventually grow under the influence of gravity to become the largest structures in the universe. The growth of structure proceeded hierarchically, with smaller objects forming first and then merging to create progressively larger systems. Individual stars formed within gas clouds. Multiple stars formed galaxies. Galaxies clustered together to form groups and clusters organized themselves into even larger structures called superclusters. This bottom-up process of assembly continues to the present day, with new structures constantly forming through the merger and accretion of smaller components. Dark matter played the dominant role in guiding this process of structure formation. Because dark matter interacts only through gravity, it was able to begin clustering much earlier than ordinary matter, which remained coupled to radiation until recombination. By the time ordinary matter could begin to collapse into structures, dark matter had already created an extensive scaffolding of halos and filaments that guided the formation of galaxies and larger structures. The distribution of dark matter throughout the universe created a complex three-dimensional network resembling a vast cosmic web. Dense filaments of dark matter stretched across hundreds of millions of light years, connecting nodes where massive clusters of galaxies would eventually form. Between these filaments lay enormous voids, regions of space that contained very little matter and remained largely empty throughout cosmic history. Ordinary matter followed the gravitational guidance provided by dark matter, flowing along the filaments of the cosmic web like water flowing through a network of rivers and streams. Where dark matter filaments intersected, ordinary matter accumulated in dense concentrations that became the sites of galaxy cluster formation. The largest galaxy clusters contain thousands of individual galaxies, all bound together by their mutual gravitational attraction. The process of cluster formation was not gentle or gradual, but rather violent and dramatic. When smaller groups of galaxies encountered each other, their gravitational interactions triggered complex dynamical processes. Galaxies within merging clusters experienced tidal forces that stripped away their outer stars and gas, creating long streams of stellar debris that traced the gravitational interactions between cluster members. The gas that filled the space between galaxies within clusters was heated to extremely high temperatures by these gravitational interactions. This intergalactic gas, heated to temperatures of tens of millions of Kelvin, began to emit X-rays that could be detected by space-based telescopes. Galaxy clusters became some of the brightest X-ray sources in the universe, their emission powered not by stellar processes, but by the gravitational energy released during cluster formation. As structure formation proceeded, the universe began to exhibit distinct regions with very different characteristics. The dense nodes of the cosmic web, where galaxy clusters formed, became sites of active star formation and galactic evolution. The filaments connecting these nodes contained smaller groups of galaxies and provided highways along which matter could flow toward the densest regions. The vast voids between filaments remained largely empty, containing only a few isolated galaxies. This spatial segregation had important consequences for galactic evolution. Galaxies that formed within dense clusters experienced frequent interactions with their neighbors, leading to enhanced rates of star formation, galactic mergers, and morphological evolution. In contrast, galaxies that formed in less dense regions evolved more quietly, maintaining their structure and star formation rates over longer periods. The formation of large-scale structure also influenced the global properties of the universe. As matter became increasingly concentrated in dense regions, the overall density contrast between different parts of the universe increased dramatically. What had begun as tiny variations in density grew into a universe where the densest regions were thousands of times denser than the average, while the voids became increasingly empty. The cosmic web continues to evolve today, though the process has slowed considerably compared to the early universe. The accelerating expansion of the universe, driven by dark energy, is gradually slowing the rate of structure formation by making it increasingly difficult for gravity to pull distant objects together. Future cosmic evolution will be characterized by the continued growth of existing structures rather than the formation of entirely new ones. The study of large-scale structure formation has provided crucial insights into the fundamental properties of the universe. By observing how galaxies are distributed throughout space and how this distribution has evolved over cosmic time, astronomers have been able to measure the amounts of dark matter and dark energy, determine the geometry of space, and test our understanding of cosmic evolution with remarkable precision. The cosmic web represents the ultimate expression of the gravitational instability that began with quantum fluctuations during inflation. From the smallest possible scales to the largest structures in the universe, the same physical processes have operated to create the complex, beautiful architecture of the cosmos. Every galaxy, every star, and every planet exists as part of this vast network, connected by invisible threads of gravity that stretch across billions of light years. Consider the remarkable journey we have traced from quantum fluctuations smaller than atoms to structures spanning hundreds of millions of light years. The universe has demonstrated an extraordinary capacity for self-organization, using only the simple force of gravity and the raw materials created in the Big Bang to construct an architecture of breathtaking complexity and beauty. As we have followed the chronological development of the universe, we have witnessed a remarkable transformation from ultimate simplicity to increasing complexity. Each era we have explored built upon the achievements of the previous one, creating new possibilities for structure and organization that had never existed before. This process of cosmic evolution continues today and will persist for trillions of years into the future, though the most dramatic changes occurred during the universe's first billion years. The transition from the Planck epoch to cosmic inflation demonstrated how the fundamental forces of nature separated from their primordial unity, creating the distinct phenomena of gravity, electromagnetism, and the nuclear forces. This differentiation of forces provided the universe with a rich palette of physical interactions that would shape all future development. The end of inflation and the subsequent cooling of the universe allowed the first particles to condense from pure energy, creating the basic building blocks of matter. The formation of quarks and their confinement within protons and neutrons established the nuclear physics that would govern stellar evolution and element synthesis throughout cosmic history. Big Bang nucleosynthesis represented the universe's first great chemical transformation, converting primordial hydrogen into helium and trace amounts of other light elements. This process established the fuel supply that would power the first stars and determine the chemical composition of the universe for hundreds of millions of years. Recombination marked another fundamental transition, allowing light to travel freely through space for the first time since the earliest moments after the Big Bang. The release of the cosmic microwave background provided us with our most ancient snapshot of cosmic conditions and revealed the tiny density variations that would eventually grow into galaxies and larger structures. The cosmic dark ages represented a period of patient preparation, during which gravity slowly organized the primordial matter into increasingly dense concentrations. Though no light was generated during this era, the foundations were being established for all the stellar activity that would follow. The ignition of population 3 stars ended the Dark Ages and began the universe's second age of illumination. These massive stellar giants initiated the process of heavy element synthesis, creating for the first time the chemical ingredients necessary for planets and life. Their violent deaths dispersed these elements throughout space, enriching the interstellar medium and enabling the formation of smaller, longer-lived stars. The formation of the first galaxies marked the beginning of complex astrophysical systems where multiple generations of stars could form, evolve, and interact within gravitationally bound structures. Galaxies became the basic units of cosmic organization, providing stable environments where chemical evolution could proceed over billions of years. Large-scale structure formation revealed the ultimate architectural plan of the universe, organizing galaxies into clusters, superclusters, and the cosmic web. This hierarchy of structures demonstrates the remarkable power of gravity, to create order from chaos, building complexity on every scale from individual stars to the largest observable structures. Throughout this entire evolutionary sequence, several key themes have emerged that characterize the nature of cosmic development. The first is the principle of hierarchical assembly, where smaller structures merge to form progressively larger ones. Stars form from gas clouds, galaxies form from groups of stars, galaxy clusters form from multiple galaxies, and so forth. The second theme is the crucial role of cooling in enabling complexity. At each stage of cosmic evolution, the universe had to cool sufficiently for new types of structures to become stable. Particles could only form when the temperature dropped below certain thresholds. Atoms could only exist when conditions became cool enough, and stars could only ignite when gas clouds cooled sufficiently to collapse under gravity. A third theme is the importance of feedback processes in regulating cosmic evolution. The formation of new structures often created conditions that influenced the formation of subsequent structures. Stellar radiation and supernovas regulated star formation. Galactic winds affected the growth of galaxies, and cluster formation influenced the evolution of individual galaxies within clusters. The transition from simplicity to complexity has not been uniform throughout the universe, but has proceeded at different rates in different regions. Areas with higher initial densities evolved more rapidly, forming stars and galaxies earlier than regions with lower densities. This has created a diverse cosmic landscape, where different parts of the universe exhibit different stages of evolutionary development. Perhaps most remarkably, the entire sequence of cosmic evolution has been guided by physical laws and fundamental constants that were established during the first fraction of a second after the Big Bang. The subsequent 13.8 billion years of cosmic history have been the playing out of the implications of these initial conditions and physical principles. As we conclude our chronological journey through the early universe, we can appreciate the remarkable chain of causation that connects the quantum fluctuations of inflation to the cosmic web of today. Each link in this chain was necessary for the next, creating a sequence of development that appears both inevitable and miraculous. The universe we observe today, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, represents the cumulative result of all these evolutionary processes. Every photon of starlight, every chemical element, every planetary system exists because of the precise sequence of events we have traced from the Big Bang to the formation of large-scale structure. We have completed our journey through the first billion years of cosmic history, following the universe from its birth in the Big Bang through the formation of the first galaxies and large-scale structures. This chronological progression reveals the remarkable story of how the cosmos evolved from a state of perfect simplicity into the complex, structured universe we observe today. Our journey began at time zero, when the universe emerged from the Planck epoch as a realm of pure energy compressed into a region smaller than an atom. We witnessed the separation of the fundamental forces and the exponential expansion of cosmic inflation, which stretched quantum fluctuations to cosmic scales and established the initial conditions for all future structure formation. We observed the cooling of the universe and the formation of the first particles, as energy condensed into quarks and gluons, which then combined to form protons and neutrons. We experience the era of Big Bang nucleosynthesis, when the cosmos became a vast fusion reactor, transforming hydrogen into helium and establishing the chemical composition that would persist for hundreds of millions of years. We witnessed recombination, when electrons combined with nuclei to form the first neutral atoms, allowing light to travel freely through space and releasing the cosmic microwave background radiation that we still observe today. We endured the cosmic dark ages, a period of patient waiting as gravity slowly gathered matter into increasingly dense concentrations within the invisible scaffolding of dark matter. We celebrated the end of the dark ages with the ignition of the first stars, massive population 3 giants that synthesized heavy elements for the first time in cosmic history. We watched these stellar behemoths live brief, brilliant lives before exploding as supernovas, dispersing their newly forged elements throughout space and enriching the universe with the materials necessary for planets and life. We observed the formation of the first galaxies, chaotic assemblages of young stars that marked the beginning of complex astrophysical systems. We traced the development of large-scale structure as galaxies organized themselves into clusters and superclusters, creating the cosmic web that provides the fundamental architecture of the universe. Throughout this entire sequence, we've seen how each era built upon the achievements of the previous one, creating new possibilities for complexity and organization. The universe has demonstrated a remarkable capacity for self-organization, using only the simple force of gravity and the fundamental particles created in the Big Bang to construct structures of breathtaking beauty and sophistication. The story we have told is one of patient development, where billions of years of gradual change created the conditions necessary for the rapid emergence of complexity. The first stars took 150 million years to form, but once they began shining, they transformed the universe in just a few million years. The first galaxies required hundreds of millions of years to assemble, but they established the framework for all subsequent cosmic evolution. This chronological perspective reveals the deep connections between seemingly disparate phenomena. The cosmic microwave background that fills all space today is a direct remnant of recombination, nearly 14 billion years ago. The chemical elements in our bodies were forged in the cores of massive stars that lived and died when the universe was less than 1 billion years old. The large-scale structure that organizes galaxies across cosmic distances grew from quantum fluctuations that arose during the first fraction of a second after the Big Bang. Our journey has also revealed the remarkable precision required for cosmic evolution to proceed as it did. If the initial density variations had been slightly larger, structure formation would have proceeded too rapidly, creating black holes instead of stars. If they had been slightly smaller, gravity would have been too weak to overcome cosmic expansion, and no structures would have formed at all. The fundamental constants of nature appear to be precisely tuned to allow for the development of complexity. If the nuclear forces were slightly stronger or weaker, Big Bang nucleosynthesis would not have produced the right proportions of hydrogen and helium for star formation. If gravity were significantly different in strength, stellar evolution would not create the stable conditions necessary for planetary systems and life. As we conclude this calm journey through cosmic history, we can appreciate both the grand scope of the universe's development and the intimate connections that link every part of creation. The story of the universe is also the story of how the conditions for our own existence came to be established through billions of years of patient cosmic evolution. The universe continues to evolve today, though at a more measured pace than during its first billion years. Stars continue to form and die, galaxies continue to merge and grow, and the cosmic web continues to develop. New chapters in the cosmic story are being written every moment as the universe explores new possibilities for structure and complexity. Looking toward the future, the universe will continue to expand and evolve for trillions of years to come. The processes we have traced from the Big Bang to the formation of galaxies represent only the opening chapters of a story that will continue far longer than the universe has already existed. Stars will continue to shine, planets will continue to form, and perhaps life will emerge in countless locations throughout the cosmos. The remarkable story we have followed demonstrates the extraordinary fertility of the universe, its capacity to generate complexity from simplicity and beauty from chaos. From the quantum foam of the Planck epoch to the majestic spiral galaxies of today, the cosmos has shown itself to be a realm of endless creativity and boundless possibility. If you found this calm journey through the beginning of time helpful for reflection or rest, consider joining us as we continue to explore the magnificent story of cosmic evolution. The universe has many more chapters to reveal, each as remarkable and beautiful as the ones we have traced together through these first billion years of existence.